Good evening. Welcome to Regents Science Live on this Thursday stormy evening here in Central New York. I'm Mr. Bertrand from Whitesboro High School, and I'm going to take you through an hour or so of review and questions in regards to earth science to get ready for tomorrow's test. Coming to you live here from the catacombs way down deep in the bowels of Utica's Proctor High School back in the TV room. So I'd like to thank a few people to get ready here. First of all, Joe Lynch in the IT Center. Thank you so much for being here and doing this for us. Utica City School District as well. Oneida Herkimer Madison BOCES, as well as our Whitesboro Central School District, who helped out with this. Dr. Belair, Mr. Russo, our admin at the high school, Mr. Kuhn, Mr. Cognetti, and Mrs. Davis for funding this and the support that you bring to the students so that they can have a little more review prior to tomorrow's test. So I'll also introduce three of my students, Madison Helfert, Danica Knapp, and Tristan Grems will be taking your phone calls and your tweets this evening to help me out so we can get through this. Okay, so from here, what I want to do is I usually start out with the most, let me do this first. Okay, your test tomorrow, June 17th, starts at noon. Be there 15 minutes early. Bring 2 pens and 1 pencil. Bring a 4-function calculator, but not a graphing calculator. No electronic devices will be allowed at entry. Look over some concepts tonight if you need to. Get a good night's rest, and do not leave any questions blank. And above all, your best friend tomorrow is your Earth Science reference table. Okay? All right. So prior to getting any phone calls, I like to start out with probably the one thing the students have the most questions about, and that is half-life. That's half-life. All right. So how does it work? Well, we're talking about the half-life, the radioactive decay of particles. And if you, and like I said, like the name says, it's half is gone in a lifetime. So after half, or after one half-life, half is gone. And each time it gets reduced by another half. So if we start out with 100 here, okay, percent or 100 of pieces, then the next one in one half-life, we have 50% remaining of the radioactive particle called the parent, and we have 50 of the daughter particle. Okay? The next one, after 2 half-lives, we have only a quarter left. Okay? And we could call this 50%, or we could call it just 50 of them. After 2 half-lives, we have a quarter of that left. Okay? There's 2 half-lives, and here's 25%. Okay? After 3 half-lives, we have 12.5% left, or we have 1/8. And then another half-life, we'd have 1/16 left, and then 1/32. And then they don't usually do anything beyond that. Okay? Well, what are we talking about here then? Let me double a little bit further. So after, once again, 1 half-life, if you, 1 and 1, 0 half-lives, you have 100. After 1 half-life, you would have 50. 1 half-life, 1 here, and half left. After 2 half-lives, you'd have a quarter, and 25 of them left. After 3, 1/8, 12.5. After 4, 1/16, or 6.25, and so on and so forth. You just divide it in half. Okay? So what would happen if they said after 2 half-lives, or how much would be left after 2 half-lives of carbon-14? Well, at 1 half-life is 5.7 times 10 to the third. And So 2 half-lives would be 5.7 plus 5.7, which is 11.2 times 10 to the third. And we'd have, there's 1 half-life would be 50%, or half, and then 2 half-lives would be 25%, or a quarter. So all you're doing for the number of half-lives is you're adding up the number of half-lives of this number here. And that should be about what they asked. Now, do you remember this over there? Yeah, they're saying yes. They're being kind, I think. Okay, so do you have that? You just keep adding this number right here, or this number right here, or this number right here. Or you can multiply it times the number. Okay, so if they got number, if they want 4 half-lives of rubidium, then you just multiply this times, what did I say, 4? If you want 4 half-lives, you just multiply that times 4, times 10 to the 9th. And then you have to figure out the number that's left out of 100, okay, or 100%. Do you see how that works? Yeah. All right, does that explain that? Okay, good. So, do we have anything yet? Anybody come in? All right, people out there, I'm doing this for you. So, start calling in. All right, so what I want to do, until then, I want to hit the top 10 diagrams. So, here we go. So the first one, celestial sphere, okay? This is the way the sun goes through our sky, okay? Now, first off, the sun will, let's talk about some days. First of all, sun rises due east, comes up 47 degrees, sets due west, okay? And this is going to be on the equinoxes. And this is going to be on 3/21 or 9/23. Okay, rising due east, rising up about 47 degrees in our sky, setting due west. All right, we're going to get 12 hours of daylight and 12 hours of nighttime on that day. Okay, remember this? From there, we've got a couple of more dates. We go to June. June's going to rise north of due east, rise about 71 degrees in our sky, come back down and set due west. Okay? Or I'm sorry, set north of west. Set north of west. So about 71 degrees. And this is June. Okay? And the sun is out. It's coming up here pretty soon. The sun's going to be out for 15 hours, and it's going to be nighttime for about 9 hours. Okay? Then on December 21st, it's going to rise south of due east, rise up about 27 degrees in our sky, and set south of due west. Okay, south of due west. And that's going to give us about 9 hours of daylight and 15 hours of nighttime. So we've got, and it goes, so all the time the sun is rising in between one of these spots on its way up. So we've got December, January, February, March, April, May, June, July, August, September, October, November, December, and it just keeps going like this, all right? Now, if you were at the equator, that sun would rise more straight up and down, like this, right? Because we're going a little lower in latitude. So, if you were to be at the North Pole or the South Pole, that sun would rise in the south, mainly here, like this, because the latitude is so high. Okay, so that is the sun's path across our sky every day. And let me make one other thing. So if we were to want, say, May, the May would rise right here and set right here. 3 o'clock in the afternoon on May would be like right here. Okay? So these are some of the common questions that they ask. Some of the common questions that they ask. Okay, any callers or tweets? Yes? Yeah? No? Okay. Usually we have some by now. All right, let me do this then. So can you hit that button? Joe, can we move that up in the upper left-hand corner? Thanks. All right, so if we're talking about the phases of the moon, okay? Let's talk about the phases and how they work. Sun's coming in this way, all right? The reason why we see the moon is because it's lit by the sun itself, just like we are, okay? And the sun's rays come in and they light up the moon. And only one side gets lit all the time, and it's the side facing the moon. Now, the reason only one side is lit up is because the moon is locked in phase. It rotates as fast as it revolves. And so with that, as it moves in its revolution around Earth, you're only seeing the back side. Only the back side gets lit up. Okay? All right. And because of that, when we are here looking, when we look, we only get a chance to see what is illuminated. And unfortunately, for this one right here, I'm going to put this as the side you don't see. Okay? So, the other side is lit. This is called the new moon. This is the new moon. All right? And the new moon, it's just, you get a glimpse of the light bending around the outside of the moon, because light will bend, and you get either you don't get to see anything, or you can see a little circle of light that's coming around the moon. Anything yet? Okay, I'll keep going. Now, in this case, we can't see this side. Let me change this. We can't see this side, and we can't see this back side. So all we get to do is see this small sliver. And it's getting bigger, so we call this a waxing, as opposed to over here, it's going to be waning. And so we get a waxing, and this is a crescent. So this is a waxing crescent, and we get to see this backside, so it looks like this. Now, you might be asking, how do I know whether it's a waxing or a waning crescent? Right? How do I know? Well, I put this bend, see this bend around the backside? It's more like an arrow going this way, or a bow bending. And that bow is open and bending towards where the sun is. So I put it like this. There's your bow and there's your arrow. And so it's a waxing crescent because it's on the right side. When it comes back, it's on the other side. That's how you know. All right? Still waiting for your calls. So, we're working on to the next one. This one is going to be called the first quarter. First quarter. So, once again, you can't see this, and you don't get to see this backside because we can't see the backside from here. Okay? So, this turns into first quarter, looks like this. That whole first quarter gets lit. Yes? All right, moving around the other one. Now, once again, this is lit, and we get to see almost this whole thing except for right there. All right, and this is called a waxing gibbous. Some say gibbous. Waxing gibbous. Okay? And we get to see majority of it. Now, my artwork is bad, as my students will tell you, right? I get all kinds of giggles when I try to draw on the board. So I should just let a student draw from now on, right? Yeah, you'll draw. Okay, so we have the waxing gibbous, which is a good portion of that. If I go like this, and we see this. Thank you. All right, and so that's what you see. So let's go down here to this, the last one over here. We still don't get to see, well, we don't see the backside, but we do see the whole thing here. And this is the full moon. This is the full moon, which and a lot of people like to celebrate that full moon as well as the new moon in myth, legend, and lore. Okay, so and we get to see the whole thing. So we get to see this. And then it just repeats on the other side. Okay, we can't see this backside here, and we can't see this, right? But this is turned around, so it's the other way. Like this. All right, once again, can't see the backside here, so this is the third quarter. This is the third quarter. This is first quarter. And then we've got the waning crescent over here. Can't see this. Can't see this whole thing. And we get to see the waning crescent. The crescent moon. Okay. Any yet? Nope. What, people? All right. So we had that. So how long? How long does all this take? It'll take about 28 days, right? That's what the number they like to use, about 28 days. So how does it work? Well, if this is day one, it's about 14 days to day two, or to around the other side, right? 21 days to here, 7 days to here. Okay, so that's how long it takes to get around. It's about cyclical and predictable. That's another thing you have to know. And I think that is about it. But it's not a perfect circle. Once again, the path or the ellipse that it takes around is not a perfect circle. All right? So at times, the moon's actually closer to us than other times. Okay, so that moon's going to appear larger then. And that moon's going to appear larger because it's closer, as all objects are. If they're closer, they are larger. So that, I think, is about it for that one. Anything yet? No? Ooh. Okay, so orographic effect. Let's move on to this one. This is where, this is one of the reasons why it's raining all the time in Seattle, I like to say, Spokane, where because of the orographic effect and those air masses, the mic, well, excellent. So go ahead and take it, and I'll finish up what I'm talking about here. So what we have here is the wind with moisture, and we're going to call this a maritime polar, so say in Seattle, and that has to rise up to come over the top of that mountain. As it rises, it expands and cools. Okay? That cloud, that moisture, it rises, expands, and cools, and then drops all that rain on this side because it can't make it over the mountain being so heavy. Then the air mass goes on the other side of the mountain. This is called the windward side, by the way. This is the windward side, and this is called the leeward side of the mountain. As it comes back down this, it warms and compresses, and it's very dry. Okay? So this side over here is cool and moist. This side's cool and moist. This side's dry and warm. And this is one of the reasons, just a little anecdote, this is the reason why the plains are so dry, because all that moisture gets dumped on the other side of the Rockies or the Cascades and doesn't have a chance to make it over. So then we get the piecing of vegetation. So in the northwest and on the windward side, there is a lot of moisture, so they can grow a lot of trees. However, on the leeward side, it's more dry and it's good for grasses. So trees need a lot of moisture, so a lot of water, so that's why there's trees there. And on the other side of the Rockies, the breadbasket, the plains, doesn't get a lot of moisture. So that's why the grasses grow. All right, well, we have a question. Who's it from?
They want it to remain in the
They wanted, okay, no worries. What was the question? What school district did they say? Okay, what was the question?
Does the storm gust tube really predict the temperature in the atmospheric pressure around it?
I'm sorry, one more time?
Does the storm gust tube really predict the temperature in the atmospheric pressure?
Yeah, so the storm glass will predict pressure, temperatures. If you have one of those storm glasses, and they react to the pressure that's going on around them. So, and different pressures will let those things float differently. But there's all kinds of ways to reduce that pressure. Hopefully, it'll reduce, the next day or so. And it's all about pressures, right? What's Bertrand's rule for life? High to low, that's how it goes, right? So we want to go from high pressure to low pressure. So look for that low pressure. Go to where it is. We have another one? Or am I carrying on? Okay. All right, so keep those storm glasses handy. You never know when you're going to need to look at them. Okay. Low pressure, cyclones, and fronts. Let me see. Do I want to do that one? Let's go to elliptical orbits. All right. Now, you probably did an elliptical orbit when you, during your lab portion, the lab practical portion of this. So, but let's take another look at this because there's some more other things we need to know. Are there some tweets? Okay. Here we go. So this is the sun. So we'll put the sun at one of these. Okay, the sun at one of these. And this is the orbit. This is the ellipse of a planet. And I'm going to put just a planet here, and I'll call it Earth with an E. So as that goes around in its orbit, okay, it goes through several different phases, if you will, several different positions, and those positions mean something, okay? So we're going to talk about, first of all, let's talk about this. So as it gets here and goes through its orbit, okay, over here it has a very high potential energy, all right, because it's not moving low potential energy, because it's not moving very fast and is farther away. So, and as it goes around here, it gains some speed because it's closer to the mass or closer to the whatever it is that it's going around. In this case, it's the sun. So as we go around the sun and we get closer to the sun, we actually get a little bit faster. Now, our orbit is not circular, and not perfect circle, but it's not very elliptical either. It doesn't look like this. This is definitely not Earth's orbit. Okay, Earth's orbit is almost a perfect circle, okay, but not quite. The evidence of that is a perfect circle is 360 degrees. Well, if it were a perfect circle, if our orbit or our ellipse was a perfect circle, it would take 360 days to go around, right? But it doesn't. It takes, 365.25 days to get around the orbit, right? And because of that, it's not a perfect circle, okay? And that 0.25, every 4 years, right, we add a day, we call it a leap year. So if it were a perfect circle, 360, it's not 360.25, okay? But it moves a little bit faster when we're closer to the sun. When are we closest to the sun? Good, very good. Maddie H says in the winter, right? So very nice, ding, ding, ding. And we are, so we're moving a little bit faster here in the winter time, but not too much. And so we're going around, and here we have a very high potential energy. Okay, very high potential energy. So we go through here, and we're going around our ellipse, okay? Another call coming in, I hear it, that's good. So what I'd also like to point out is Kepler's, a couple of Kepler's laws, okay? Kepler said things work in circles. And when he looked up, he said they come around, so it must be a circle. And this was in 1624. So Kepler was pretty brilliant at the time, and he took measurements of when all this occurred, okay? And then he said that these areas mark out equal time, okay? So if I were to do this, this is the same as this. the area inside those are the same. Marks out equal areas in equal time. But because of that, it could travel faster because it has to make this distance faster than it has to make this distance. It's rotational mechanics. So it has to travel here, travels a little bit faster than it does here. So as we make our way around this, it's going fast, slow, fast, slow, fast, slow. But it marks out equal areas in equal time, the harmonics of the universe. And that's what Kepler gave us way back in the 1600s. All right, so since we have a phone and message, what do we have? Danica, oh, Tristan.
Someone asked, what is the equation for eccentricity?
Okay, so any equations you need, check your, thank you so much, check your science reference table, and they'll be right here. So, right on the front, here's your equation for eccentricity. Here's your equation for gradient. Here's your equation for rate of change and density. So if you need those. All right, so what do all these mean? So E equals D over L, which is us throwing a number. So D is distance between the foci. So if you've got your ellipse here, this is your distance between the foci. So let's call this 5. And then you've got the length of the major ellipse, which is L. So you've got D over L. And so you got, let's call this 10, right? And so we've got 5 divided by 10, which will give us a decimal. Always has to be a decimal. Okay, so that's that. And then gradient is field of change is change of field value over the change. Let me do this over the change in distance. Okay, so let me give you an example here. If you've got a topographic map, all right, and you've got a point here and a point here, and the contour interval is 20. So if this is 0, and so 20, 40, 60, this would be 60. So we've got the field, that's 1, so the change in field value is 60. So we have 0 divided by, or 60 minus 0, which would give us 60 over, and then you're going to have to use the scale that's given on the on whatever map you're using. Only use the scale on the map you're given. Only use the scale on the map that's given. Okay, don't use any other measuring device. So if this is, let's say, 2 kilometers, it's 60, and the field value, let's call this 20 meters. Let's call it 20 meters. Okay, so it's 20, 40, 60 meters divided by 2 kilometers. Okay, so 60 divided by 2 is 30 meters per kilometer. And that's how you'd figure out gradient. Okay, rate of change is the same thing. How much, so that would be, say, how much, I can't even think of an example, how much pennies I can collect in 1 hour, okay, if I can, in the time. So pennies in 1 hour, if I collect 5 pennies in 5 minutes, okay? So 5 times 5 would be 25, okay? And then you divide it by the hour. Okay, so that's that, and D equals M over V. I think we've done that quite a bit, so mass over volume. And they might ask you to find the volume, right? Let me do that. So let me go back to here, and where D equals M over V, right? And I taught you to put D in the house. So we're going to do this over this and here. Yes, D equals M over V. So D equals M over V, V equals M over D, and M equals D times V. So however you need to do this, it's pretty easy. D equals M over V, V equals M over D, M equals D times V. Whatever you need to do. And they'll give you some number. They'll give you 2 of them. All you need to do is find the other one. Okay, so we have another phone call coming in. Danica, what do you think? We have 3. We're 3 deep. So give me the first one.
What's the difference between porosity and permeability?
And what?
Permeability. Okay,
porosity versus permeability. Excellent question. Let me do this. All right. So porosity. So you've got beads, yes, or uniform sedimentation, uniform rocks at the bottom of a yes, the uniform rocks at the, let's just put it on the ground, okay? And those rocks have pores in them. So the porosity is the amount of pore space that you have. So you can have little rocks that are all the same, or you can have big rocks that are all the same, and that porosity is going to be the same. Size doesn't matter when it comes to porosity because the holes, if they're uniform, right? We want to say if they're uniform. If they're not uniform, then you've got some flat things sitting in here, and they're not sorted, right? So these would be sorted and uniform. And if you've got some flat things in here, that packs it down. That will pack that down. And as it packs it down, then the porosity will decrease, okay? So what is permeability? So permeability is the upward movement or the absorption of particles. So what happens is, as you get smaller, the particles here become closer together. So let me twist this and go like this. What happens is that water gets pulled up like this. And the smaller, because water has water has some properties. It's very cohesive and it's very adhesive. So it adheres to things and it wants to bring everybody with it, all the other water molecules, right? It's like, and I use this as an example for my students. If they're standing out in the rain like you would be if you're outside now, and you're just standing there and your pant leg is near the ground or touching the ground, that water will start to seep up. That's capillarity, okay? And that seeps up here. So now, permeability is that ability to, is the ability of water to go inside, okay? So the closer the particles are, so let's call this porosity so I don't get mixed up, and permeability and capillarity. All right. Permeability is how closely tight packed the particles are so water can go down inside it. Okay? If I were to spill water on this versus spill water on even this stone, okay, that water's going to be able to seep in here because there's pores here, but it won't be able to seep in here. So this is permeability. Okay, it's the ability of water to go in. This is capillarity, the ability for water to go up. Okay, smaller particles. And this is porosity. Okay, good. Thanks for that question. Who was that, did they say? No? All right, no worries. Next.
How does the Earth's interior work?
All right, how does the Earth's interior work? So glad you asked. All right, let me pull a Hunter Smith. Shout out to Hunter Smith. Thanks for calling in, buddy. How does it work? All right, let me see if I can find a picture here to work from. So before I go ahead and draw, I thought I had a whole mess of them. They must be in here. Okay. Let me find that picture of Earth's interior. If I can do it quick. I guess not. Okay, let me flip to Earth's interior. Blank sheet. Here we go. Earth's interior. Here's the top side of Earth, right? And this is the lithosphere. Let me move this up. This is the lithosphere. This is the place we walk. This is the troposphere, the place we breathe. Okay? And this is underneath this is the crust, and this is the asthenosphere. also called the plastic mantle. And then inside here is the Stifer mantle, and then the outer core, and then the inner core. Okay, so the inner core is solid. It's made of it's iron and nickel, and let me throw this up. This might be better. Can we see that okay? Is that better? I'll show both. All right. So if you're turning your Earth reference table, this is one of the best places to look and get a glimpse of this. Okay, let me run through this again. So we've got the inner core, whose density is 12.8 to 3.1. Then we've got the outer core. The densities go out as you go, or get less as you go out. And that's because when Earth was in its infancy, it was spinning like crazy. And as it did that, the heavy stuff went down and the light stuff went out. And as that light stuff went out, we got a crust, and we have a hydrogen that got released, and chemicals and carbon dioxide and methane, and all the stuff that's inside of Earth got a chance to come out. Okay, and then they started to mix, and H2O, and we have water. So we've got the inner core, the outer core, the Stifer mantle, and that has a very low density, but the lowest density belongs to 3.0, which is the basaltic crust that's in the ocean, underneath the ocean. Believe it or not, it's not all sand. It's a very dense, seemingly dense, oceanic crust. And then on top of that is the granitic crust, which is the granite which starts all of the makeup of our soils, right? And so that comes out. All right, so what happens is, underneath here, this is the asthenosphere, okay? This is the plastic mantle. This is the lava. And lava wants to get out because it's under high pressure. And so Bertrand's rule for life again, high to low, that's how it goes. It wants to get out, and it spews itself out like this. And when it does that, okay, and it does so in this zone, this is called a divergent zone, and it pushes out and starts to make new land. And this is in the middle, the mid-Atlantic ridges, or any ridges in the middle of the ocean, or a couple places actually on Earth. And also, okay, so it's pushing out there. So that's one spot, okay? Then we have over here, so this is the Mid-Atlantic Ridge. Let me point to that on the Earth Science reference table so you can use this as a reference. And then we have over here, near the Cascades, we have a trench. And that trench is called a subduction zone. So this is a divergent zone. This is a subduction zone. This is where it's subducting. You're going up underneath. All right? So, and that is where these get pushed up. Okay? So it goes underneath, and we get some mountain building here. And that mountains are because this wants to get back out, so it shoots up and creates mountains. Okay, it also moves plates all around. All right, and that's the reason why we have plate tectonics, is because of this always destroying and creating new. Okay, so Pangea will return again. Let's reunite. All right, so also let me point out here that this is the pressure. So as you go down in depth, pressure increases. Here's your atmospheres: 0 atmosphere, 1 atmosphere, 2 atmospheres, 3 atmospheres. All right, we saw millions of atmospheres, not just one, millions of atmospheres. It's like when you go down in the ocean and you're scuba diving, or even deep sea with just a snorkel. All right, you feel that pressure. That's atmospheres, 1, 2, 3 pressures, 3 atmospheres of pressure. This is in millions of atmospheres. And then also as you go down, the temperature also increases. So you just got to find what depth they're giving you and go up and find out what the temperature would be. Okay, and that's probably all they'll ask there. So that's how it works, Hunter. I hope that answers your question, and get a good night's rest, and we'll see you tomorrow. Shout out to the Smith family. Next.
Somebody wants you to show them a geocentric model.
Sure. Geocentric model. Geocentric is the non-Copernican model. Copernicus said, hey, I don't think this is right. I think that we are a heliocentric model, which means Helios was a Greek sun god. And so that heliocentric model is the Earth going around the sun. Well, prior to that, they said that the Earth actually, everything went around the Earth, but they really didn't have a good way to describe how that happened, at least mathematically or visually. So the geocentric model states that the Earth is at the center and everything else goes around it. Well, Copernicus says that doesn't work out mathematically, and it doesn't work out visually either. So it makes planets disappear in retrograde. And so he said that doesn't work. So Copernicus was the first one to say that that's not correct in his thesis, De Revolutionibus, 1600s. And then Galileo restructured that, right? He says, yeah, I think Copernicus was right, but so did Bruno. And that's why Galileo got in trouble, because he believed in the Copernicus method or theory, and now it's the accepted theory of the day. So, hope that answers the questions. Next.
Your daughter asked.
My daughter, shout out to Colette, my daughter, and Miguel, and everybody out in Buffalo. Thanks for calling in. By the way, let me just say that she tweeted. Okay, she tweeted. She was with me when I did this the first time, which was 10 years ago. This is my 10-year anniversary. So Mr. Putnam, the eminent Mr. Putnam, texted me last night, we did this for 25 years, and said, I think this is your anniversary. So she was with me the first time. She was actually taking the test that year, so it was my first year to do it, and she sat where you guys are. So what's her question? I'm surprised you have a question. Wait a minute. You're my daughter? Go.
She said, can you explain the difference between cumulonimbus clouds and stratus clouds?
Okay, so yes, so cumulonimbus clouds is what we're getting possibly right now. And it was so funny because as a young child, I'm going to expose this. She used to call it a cucumber nimbus cloud. I still share that story with you all, right? And so it's just a way for them to remember. So what I have here, let's talk about the cumulonimbus cloud, what that is versus a stratus cloud. So we've got low clouds, and let's call this, here we've got middle, let's make this like this. Then we got middle puffy clouds, and then we got high wispy clouds. Okay? These are cirrus clouds, and these are cumulus clouds, and these are stratus clouds, usually, give or take, right, about the height. Clouds are usually named from where they form in the sky. However, today was a great example. We had, I didn't get a chance to see it, but I'm assuming we had a cumulonimbus cloud, because what happens is we have a cold front. We have a cold front, which is what we had coming down from the northwest. And that cold front was moving like this, was moving pretty quickly. And it's very high pressure. The rule is, don't forget, Colette, cold and drier, never higher, right? And once again, Bertrand's rule for life, high goes to low. And we had, this is the heated, this is what we had, and this was a low pressure over here. So what happened is that cold front, let me push this up, that cold front moved in very quickly, and those clouds had a chance to form, not very slowly. So they got pushed up, and when they get pushed up, they make this anvil cloud here on top. And this is a cumulonimbus cloud. Cumulonimbus, okay? And it's a column of nimbus. Now, normally what you get in these stratus or the low clouds, what's called the nimbus cloud, and that nimbus is rain, okay? And I tell my students to bring on the storm because Harry Potter wrote a Nimbus 2000, I think. He brought on the storm, right? A little information there. So that creates this cumulonimbus, and that rushes up like this, and then this gets cooled very quickly. We get the high pressure dropping down, the low pressure pushing up. Let me do this again. Here's that anvil cloud, and we get the high pressure dropping. We get the low pressure pulling up. So let me go through this. So normally winds happen for differing pressures. We've got the high pushing on the low. So we normally get this shear, right? Just one pushing on. The bigger the gradient, the more the powerful the wind, right? The bigger the gradient between the high and the low. So we get that moving one way, and we get it rushing on that low pressure, and sometimes what happens, that goes vertical. So we get the shear from the side, and it goes up like this. And when it goes up like that, then we've got a hurricane or a tornado, okay? And tornado on land and hurricane over water, right? So what happens is we get this, that high pressure flowing down, that low pressure pulling up, and then it starts to get more, that low pressure pushing up like this, and we also get one inside here, and we get that tornado. That's why we get the pull up, and you can get pulled up in a tornado because of the differing pressures, and then, get taken away. All right, cumulonimbus. Thank you, Colette, for calling in. Shout out to the family. Next, what do we have?
Ava and Bianca have a question.
Oh, Ava and Bianca. Shout out to you all out there, my students. Thank you so much for calling in. What is your question over tweet?
How do you identify a rock?
Sure. Okay. How do you identify a rock? Now, you're not going to have to necessarily identify a rock, but let's talk about the features. All right, so let's talk about this one, this one, this one, and this one. All right, so I tell my students the best place, and we took a walk. We take a number of walks throughout the year, and this one, we take a little jaunt, and they drop some of those different rocks like you see at the drive-ins, Dunkin' Donuts drive-ins, right? You can look out the window as you're ordering, and you look down. It's a perfect example of just about every type of rock there is, because there's igneous, metamorphic, and sedimentary sitting there. How do you know? Okay, here we go. Here's sedimentary. And it's sedimentary because it has sediments in it. See? All right. This one's also sedimentary. How do I know? Well, do you see the layering? And also, it's somewhat smooth, right? It's not necessarily, it feels like sand. So if I go over and I go to the Earth Science reference table right here, and I go to, here is our rock charts that you can use. Don't forget, this is your rock cycle. This is how things are cyclical and predictable within the creation of Earth, the rocks that are on Earth, in Earth, and all the other places, okay? So first it comes out, it's magma right here, and then it solidifies, it turns into an igneous rock. Then it can get weathered and eroded, and these sediments can get buried and deposited. They can get compacted and turned into a sedimentary rock. Then they can get transformed by heat and pressure into a metamorphic rock, or then they can melt and turn to magma. Or they can take any one of these and go in any one direction, one from the other, okay? So go back to where it came from. So how do you tell? All right, well, what they're going to ask you to do is maybe use this chart here, which is the igneous rock identification. Remember, we colored all this in. We've glassy, fine, coarse, very coarse. And that refers to, say this. This is an igneous rock, right? It's very coarse grained. And coarse has to do with the size of the particles, not what it feels like. Size of the particles, okay? So, in that case, here's the same thing. Size of the particles, okay, and you can see it's got some pink in there, and that pink belongs to the potassium feldspars here, and the white and the black belong to the biotite, and the gray, the paleoglazed feldspar, and the clear belongs to the quartz. So it's got all these in it, okay, and it could have a percentage of that. Don't forget, what's the composition? Is it felsic, which is the stuff on land, because you can feel it. That's what I say. It's felsic. And then mafic, mainly underneath the ocean, right? You can't really get to it. Basalt is a good example of that. All right, don't forget about the lower density, the higher density, lower density, and lighter color and darker color. Okay? It can also be glassy as well. It doesn't look like I brought one. All right, it can also be glassy as well. And this would be an example of glassy, although this isn't exactly an igneous rock. But obsidian would be a good example of glassy, okay? And don't forget, if it has holes in it, it's vesicular, where the gas pockets were, and the gas shot out or escaped, and it causes those to shoot out of the volcano, which makes it extrusive, okay? Extrusive versus intrusive. Okay, so let me go over here, and you can see, so in the sedimentary ones, we have conglomerates, okay, which would be this one. And we have breccia, sandstone, siltstone, and shale. And those are different comments about what size the particles are inside. Classic means it has made up of particles, pebbles, sand, silt, and clay. Or it could be crystalline, which would be some of the rock salt, the rock gypsum. If it's somewhat clear, I didn't bring this would be somewhat of an example, okay? Be a little lighter than that. Let me pull this out if I can. Aha, yeah, these are kind of mixed up. Okay, that's a good example of crystalline, okay, structure. Rock of crystalline structure. Okay, and then the metamorphic rocks. Here's an example of a metamorphic rock right here. You can see the banding of the minerals, and that's a good example. And that would be gneiss here, and it's got, it looks like that map symbol, right? This one here is schist, right? It's got the platy mica crystals visible from metamorphism of clay. So that is a metamorphic rock. And I hope that helps, unless you have something more questions. Okay, I'm getting the signal here that we have a lot of questions coming in. So I'm going to try to maybe move a little bit quicker and get to all the questions. Next, who is it and where are they calling from? What's the question?
Hunter asked again.
Hunter, ask again.
He wants to know about the high density and rocky composition of terrestrial planets.
Okay, so terrestrial planets. What you need to know is the terrestrial planets are the inner planets, and then the Jovian planets are the outer planets. And those, you can look here at the solar system data. Once again, go to the Earth Science Reference Table. Notice I'm always going there because 70% of your test is on that. So here is your mass and your density, okay? And the inner ones all have a high density, and the outer ones all have a low density. And Saturn, if you put Saturn in water, it would float because its density is below 1. And here's your high density ones, okay? So once again, same thing as with the Earth core, as the protoplanet was being formed and the solar system was being formed, those heavier planets went to the inside and the lighter planets went to the outside, or created lighter planets, I should say. Hope that answers your question, Hunter. See you tomorrow. Question?
Could you explain cold and warm fronts?
Cold and warm fronts. And is that somebody that we know? Shout out to anybody? Anonymous. Sure. Cold fronts and warm fronts. Yes, let me do that. And if I can switch to this, I think I have one in here. Cold front versus warm front. Let's do this. Yeah, we'll use this. Okay. This is something that we see happening all the time. It's called a mid-Atlantic cyclone. And that cyclone moves inside, right? It's a cyclonic action like a Dyson or like a Shark Navigator, if I can use those, right? So it's that cyclonic action that pulls stuff up because what's happening is the low pressure is coming up and that high pressure is diving down, okay? So if you were to look at this, let me go here. This is going to be, this happens all the time, is that high pressure drops down out of Canada and gets pushed by our southwesterlies, our prevailing southwesterlies, moving this way, okay? We get that moving up here towards the northeast. And this is why the Ohio River Valley, or the Ohio Valley, all the way up through here, the Carolinas, Tennessee, Kentucky, and that whole area have such a lot of rainfall because that gets pushed up this way, okay? So, cold front, let me do this. Let me get another one here. Where's the light colored one? All right, so this is the cold front right behind here. Here's the warm front. It's raining pretty good right here. All right, here's going to be warm and moist too. And right here's that cold front. So we're going to get rain right here. We're going to get a lot of rain right here. Here's that low. What you have lots of times is either a small or a large occluded front, which is where they're with each other. Okay? And that cold front's moving this way. It's going to be cool behind here. Warm and moist in here, and definitely warm in here. Okay, this is that warm front that's overtaking a little bit of cooler air. And as it's overtaking the cooler air, let me do this. This is the length of a warm front. This is the warm front here, and this is a little bit cooler versus a cold front, which would be, what am I doing? That cold front would be a lot shorter, overtaking the warm front. Okay, and here's that cold front moving in. Okay, notice the difference in line. So we get all this area, hundreds of miles of rain perhaps, and here would be a shorter distance, 5, 10, 15 miles of a rain coming down. Okay, I hope that answers your question. By the way, you can always find that warm front and cold front information on your science reference table. And let me find that right here. Okay, this is all of the information you're going to need for your station models. And we have also your temperature conversions and your pressure conversions. Okay, so I hope that answers the question. Let's move on. Let's get to another one. What do we have?
My sister called in.
Your sister called in. Okay,
Yeah.
shout out to your sis.
Yeah.
And what'd she ask? Is she taking earth science?
She's in 6th grade.
Okay, so what's her name?
Sophia.
Sophia. Hey, Sophia, thanks for calling in. Your sister's sitting right over here. So what's your question?
She wants to know about convection current.
Oh, wow. Okay, so convection currents that control everything that goes on. Pick it, right? On top of Earth or below Earth. Change happens because of convection currents. And convection currents happen because of high or low pressure. That's what we get. So let's talk about this. On top of Earth. And I'm going to find this here. This spot in your Earth Science reference table, convection currents. What happens underneath Earth? Convection currents. What happens in the ocean? Convection currents. It's all high to low. Okay? High wants to push on the low. So on top of Earth, let's do this. Here's your top of Earth. We have warm, moist air that rises and goes up and gets cooled and then drops back down. So here's the low pressure, here's the high pressure, and it just keeps doing this. And these happen all over the world. They're called gyres. And we get them. Let me go back to this. Here's the planetary winds. And we have these cells that happen all over Earth. So here we have, let me switch to this so I can write on this. Where are you? Right there. Okay. All right. So we have this warm, moist air rising at the equator and goes to 30 degrees south, cools and drops. And it's dry right here because it released all that moisture before it got dropped over here. So it's making this cell. And then this cell is rising and dropping itself. And then there's another cell that drops here. So we get wet, dry, and wet. Okay? And wet and dry, and wet and dry. And don't forget the wet, and then the dry here. Okay? So it works in those cycles. Okay? And these cells happen all over Earth, and they transport different moistures all over Earth. And this is what we experience as our weather and our climate. Okay? And sometimes that changes due to El Nino or La Nina. We are in a La Nina year, and that's affecting a lot of the climate and the weather. Okay? And you can look that up as well. That's just the change in water that it happens in the Pacific Ocean and affects everywhere else, because the Pacific Ocean is the largest body of anything on Earth. Okay, so there's that. How about underneath? Well, underneath Earth, same thing. Let's go underneath. We've got the asthenosphere, like we had before, right? Like we talked about before, and we have the movement of lava, right, that comes under pressure. It wants to find a way out. It finds a way out in these divergent zones and then gets pushed out. So these convection currents happen underneath Earth in the asthenosphere, which cause the plate movement, okay, which causes new rock to be formed. And then from new rock being formed, then we get sedimentary rocks and metamorphic rocks. And so we got the rock cycle. And we also have the weather cycles from on top. Okay? And the breakdown of materials due to either being cold or warm. So we've got surface processes that are also affected by this convection currents. So I start my whole year out, we talk about convection currents and high to low. Didn't we do that? Excellent. What do we have next?
See, Jacob wants to know how I identify as schist rock.
Okay, Jacob, schist. What? Lexi Jacobs. Okay, Lexi. Is she from wherever you're from, Lexi? I'm not sure. Frankfurt, sure. How do we identify schist? All right. Schist has platy mica crystals in it that form from high pressure of clays. So clays get crushed down, and you can see it right here. Let me point to it. Platy mica crystals visible from metamorphosis of clay or feldspars. All right, so that's what's inside there, and that gets crushed and ends up like that. And New York is pretty famous for its New York schist, which if you go down, and I discovered this on a vacation once. I was down in New Jersey, actually looking over to New York, and you look down over the embankment, and there's this New York schist that's all over the place because of the crushing of the plates when one plate ran into the other one. And so that's where we get from that. Okay, so you can find that a lot in New York, especially down near the city where they've excavated a lot of areas. Okay, I hope that helps. Next.
Absolutely.
Show the phases of the moon diagram.
Phase of the moon diagram. Yes, let's do that. Let's do that again. Okay, let me get clean here. And phases of the moon diagram. I think there's one in here. There's not. I will create another one. Yeah, maybe not. All right, no worries. Phase of the moon diagram. Here we go. All right, so did they say exactly what phase of the moon? They
I just wanted to know the diagram.
the diagram. Okay, so run through it again. You think? Okay, so let me run through this real quick. I did this earlier. I won't take too much time on it, so we can get another phone call in. Do we have others? Other questions? Okay, so let's do this. Here's that. The sunlight coming in this way, right? We only get to see half. You only ever get to see half. And the lit side over here is the half you get to see. Okay? So we see this. And there we go, just like that. Okay, we get to see only the half. Now, so the sunlight's coming in here. Here we don't get to see anything really, or we get to see some of that sunlight's bending around. So once in a while you get to see just that. This is called the new moon, right? This is called the new moon. And then here, as we're sitting here or standing here looking out, we get to see only this small portion right here as we look out. So this turns out this is going to be the crescent. This is going to be the waxing crescent. Here's the first quarter. Once again, we only get to see half of it, so we don't get to see this back half because we can't see around the other side. And that's going to be a quarter moon. And then this one, we get to see a little bit more of that. This is called the waxing gibbous on this side. So it takes about 7 days to get here, about 14 days to get here, 21 and 28 days is what they like to reduce that down to. And so here is your full moon. Here is your waning gibbous, third quarter, and waning crescent. Waning means to go away or to disappear, so it's waning away. So that's that. Those are the phases. Once again, that's a crescent, first quarter, waxing gibbous, full moon, waning gibbous, third quarter, and waning crescent. Once again, you can't see that backside, so all you get to see is, and don't forget, it's going to be on this side now, on the left side, as you're coming back around. You're going out, it's on the right side, the other side is back. That's how you know. So when they ask you what the third quarter looks like, make sure you're here and not here. Okay? All right. I think that answers that question. Yes? Got that? Next.
Someone wants you to explain longitude and latitude.
Sure, let me do this. Longitude and latitude. Here's Earth, right? About 1880, there were as many as 19 different lines of longitude are places where time begins. So we basically use longitude as to mark time so that we know on different places on Earth what time it is. So let's do this. Here's your equator, yes? That equator is at 0 degrees. And up here, these are 90s. And what that represents is latitude as you go up here. And they're usually done by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90. Okay? 90 degrees north, 90 degrees south. And the way we measure that is we look at the North Star, right? And we take our measurement to that North Star from wherever we happen to be. Whatever this measurement is, let's say it's 43 degrees, as we look up at the star, that 43 degrees is your latitude. And that's how we know. And as we go up or down here in this area, then that altitude to Polaris either goes up or it goes down. That's 0. That's where we'll see the North Star on the horizon at the equator. And then as we get to the North Pole, we'd have to look straight up. It's 90 degrees. Okay, now the same thing is done in the Southern Hemisphere, except they can't use the North Star because you can't see it. So they use what's called the Southern Cross, a famous song made famous by Crosby, Stills, and Nash. All right, so we also have that same thing going on here. So that's latitude. Now latitude runs east and west, but measures north and south. Remember that because we have lines of longitude which run north or south, but measure east and west. Well, east and west and what? Everything needs a start point. And the start point in this case happens to be the prime meridian, which is in England. Okay, so I don't know if I can draw this very well, but this would be Africa, and this would be England, and this would be 0 degrees. All right, and then these are usually supposed to be set up at 15-degree increments because the Earth is a circle, so it's 360 degrees around. It takes 24 hours to go around, so 360 divided by 24 is 15 degrees per hour. That's where Earth rotates. So, if I can use this, bring this in. Earth rotates at 15 degrees per hour. Oh, yeah, they're right. Thanks. It's 15 degrees per hour as it rotates around, okay? It's divided into lines of longitude at 15 degrees and lines of latitude as measured north and south of the equator, okay? So what you also want to do is, let me see, remember that, so your longitude is the number of longitude lines away from Greenwich, England, okay? And we are 75 degrees or 5 longitude lines away from Greenwich, England. So we're 75 degrees west. Now, every one of these gives us a time zone. So there's 12 on one side, and there's 12 time zones on the other side. And it's all measured from the prime meridian, which is in Greenwich, England. So you can go, and where that ends up is 180 degrees around the other side. So what we get here is we get the east and we get the west. And we live in the west, okay? And then there's the Middle East and the Near East, and then there's the Far East. Near East, Middle East, Far East. The Middle East, as you know, is the countries in Iraq and around the Red Sea. And then Far East is over in the Orient and Japan and China, okay? And so, incidentally, I tell my students, and that the name they gave Japan, which is the first country to see the sunrise, is the land of the rising sun. And that's the reason why, first civilized country back then when they set it to see that rising sun, okay? So that's why they call it the land of the rising sun. There are 24 time zones, 12 on each side, and I hope that answers your question. Next. Yes?
Bianca said, how do you tell the time of the day based on latitude and longitude?
How do you tell the time of day based on,
Latitude and
Well, no, you can use the sunlight.
Like whenever you said
Okay, so you can use you can use it, and so I take them outside and I ask them, well, okay, what time do you think it is? And we base it on where the sun is in the sky, right? And if it travels at 15 degrees per hour and it rose at 6, say the sun rose at 6 and it's 30 degrees off the horizon, it's 2 hours later. I think that's what she's asking. It's 2 hours later, so it would be 6, 7, 8 o'clock, okay? Or if it's 30 degrees on the setting sun, if it's setting in the afternoon at 30 degrees left off the horizon, that means it has 2 hours, okay? So if the sun's going to set at 6, it's 4 o'clock in the afternoon. So that's how you can tell. And I'm glad I challenged you to remember that when I took you outside. Next question.
he wants you to identify the mineral granite.
Who does?
Anonymous.
No, anonymous. Wants me to identify granite. All right. Granite is very coarse grained. This is a piece of granite. It is coarse grained. It is light colored, and it is light as well. It's not very dense, and so those are the characteristics that you would use. Okay, and let me go back if I can put my hand on your science reference table. We're going to go over here, science reference table. Where are you? And we're going to go to the granite. Okay, so we're looking at granite right here. Now, granite would be intrusive. Don't forget, tomorrow they're going to give you clues. They're going to give you words and clues to find it. So all you need to do is refer to this. So they might give you lighter, lower density and mafic with quartz, paleogauss, feldspars, and biotites. Well, it's in this area right here, so you can go up here, and it would be granite. Okay, so that's one way to do it. Well, probably the best way to do it. Okay, and they could say coarse-grained, non-vesicular. So coarse-grained, non-vesicular, light-colored, and you're in granite. Okay, just use the chart. Next question.
I have a question.
Sure.
He said sequence of events for rock outcrops.
Oh, okay. This one it plagues students all the time. And what it's asking is, how do you know what sequence of events are happening in any type of rock outcrop or a piece of rock that you might see? So say you're traveling down to Albany, and as you travel down, there's those rock outcrops. Well, how do you know what's going on? Well, the law of superposition, one, says that everything on the bottom or the top, everything on the bottom is first. So this was laid down first, right? Sedimentary rock, say it was laid down by a river, and this was first, okay? And so we go up, and this is the next one, okay? And this is the next one, and this is the next one, and this is the next one. But what can happen is a fault can occur where this one goes down, okay? It subducts, goes underneath. And which means that this one and this one match each other. So you have to know that these were here first, these were all laid down first, and then the fault occurred, okay? Or suppose you have an unconformity in here, right? Well, that unconformity had to happen before this, otherwise it wouldn't be part of it. Or say that you have an igneous intrusion where you have a spike of igneous rock or a lava, which then would be igneous as it cooled. Well, that igneous rock had to go through, that igneous intrusion had to go through all of this. So all of this was here prior to the igneous intrusion, prior to the lava flowing up. Okay? So law of superposition. First of all, law of horizontality says everything was laid down horizontal. If it falls, it's flat, it's horizontal, right? If it's not horizontal, something might have happened. Such as if some of the rock, it looks like this is folded. That is plate tectonics, dynamic or crushing of Earth, right? And that rock could be crushed, all right, due to metamorphic or some sort of plate tectonics. I hope that answers some of your questions. You have to really take a look at one, but these are good rules to try to apply. Okay, good. Next question. That's it? That's it. Well, I think then it's going to be a wrap. If we have no more questions, nobody else is calling in. So I thank you so very much for watching this evening. I hope that this helped. I would like to thank those I thanked at the beginning, Utica City School Districts, Joe Lynch over here, Whitesboro Central Schools, OHM BOCES, and all the administrators for putting this together, because I hope it helped. And I also like to introduce my helpers for the day. So Danica Knapp, come on over.
Wait, can they just come with me?
And you can all come over at once. And then I've got Tristan Grems, who volunteered to help today. I think you need to come over just a little bit more. And Maddie H., come on over. Okay, so these are my students that I had the pleasure of spending, let me go this way a little bit, I had the pleasure of spending the year with and get harassed all year long. So thank you very much, ladies. I appreciate you volunteering to do this. It was totally voluntary, and I certainly can't do it without you. So you all ready for tomorrow? They're ready for tomorrow? Okay, good enough. So thank you so very much. Appreciate it. You have a great night. Get some sleep, and good luck on your test tomorrow. See you later.